Welcome to Math TV with Professor V. In this video, we're going to be finding Taylor and Maclaurin series for functions. The purpose of this video is just to help you crank out a bunch of problems. If you want more context and background and a lecture regarding Taylor and Maclaurin series, then I'll link the video here. That's on my Calculus 2 video lectures playlist. Okay, so let's dive right in. You just got to put to memory the formula for Taylor and Maclaurin series. They're basically the same formula, right? So we have a function f of x. If it has a Taylor series representation, we write it as follows. So we have the sum n equals 0 to infinity. I like to break down each term into three parts. We have the nth derivative of f at a. They're going to tell us what a is. Then we have n factorial in the denominator. And last but not least, you have x minus a raised to the nth power. And so if you write out the first few terms, it looks like we have written here down below. This is for n equals 0. This is for this entire term right here. This is for n equals 1. This is for n equals 2, n equals 3, etc. Now, only difference when you're dealing with a Maclaurin series is that a is equal to 0. So really you just have one formula to memorize. So again, you have f of x represented as the sum, n equals 0 to infinity. We've got the nth derivative at 0, since that's what a is equal to. We have that n factorial in the denominator, and then x minus a in this case is going to be x minus 0. So all you have is x to the n. And then same as before, this is for n equals 0. That first term, n equals 1, n equals 2, etc. So here's how it works. When you're trying to find a Maclaurin or Taylor series representation for a function, you're going to be given f of x and given a. And then you start out by listing each of the terms according to the formula. And your goal is to pick up on whatever pattern is going on so that you can write your final answer, your final series using sigma notation. Okay, so we're going to list it out term by term until we have a good sense of what's going on with the pattern that we can write everything in sigma notation. All right, we're going to start off doing a few examples just with Maclaurin series. So a is 0, they're a little bit easier, and then we'll do some Taylor series, okay? All righty, so first the directions will say something like, find the Maclaurin series for f of x using the definition of a Maclaurin series. So applying this formula here. I'll talk more about other kinds of exercises you can do where they do not require you to use the definition later at the end of the video. Okay, so f of x is equal to 1 over 3 plus x. Let's start off by making a table. You're going to list out what n is, then the nth derivative at x, and then the nth derivative at a. In this case, since we're finding a Maclaurin series, a is equal to 0. Okay, there's no exact rule as to how many derivatives you need to take, just enough until you can see a pattern emerging. I usually start with at least 3. 0, 1, 2, 3. So the 0th derivative is just f of x itself, right? Which is 1 over 3 plus x. I'm going to write it as 3 plus x to the negative first because I want to get it rolling, so I'm ready to take the derivative in the next step. And then now I'm going to substitute in 0 for x. So this is going to be 3 to the negative first, which is 1/3. Okay. Next, let's take another derivative, or let's take our first derivative. So minus 3 plus x to the negative second. And don't forget, you do have to use the chain rule. So I have to multiply by the derivative of 3 plus x, but that's just 1. So I'll list it out here so you know I thought about it, but it's not going to affect things. And then if I substitute in 0 for x, then this is negative 3 to the negative second, which is negative 1 over 3 squared. I typically will not multiply out everything because it makes it easier to see patterns a lot of the time. So instead of 9, that's why I wrote it as 3 squared. So I can kind of pick up on what's going on with each of the terms. You'll see in a minute. Okay, second derivative time. Now we're going to have positive 2 times 3 plus x to the negative third. And I'm going to substitute in 0 for x. So this is 2 times 3 to the negative third, which is 2 over 3 cubed. And then let's do one more. So if I take the third derivative, then I'm going to have negative 6 times 3 plus x to the negative fourth. So if I substitute in 0 for x, this is just going to be negative 6 over 3 to the fourth. All right, very nice. Now all of these values here, 1, 2, 3, 4, these are the nth derivatives at 0. So this is just one of the 3 parts of each of the terms. Remember, I highlighted in blue here, the nth derivative at 0. Now we're going to start listing term by term the Maclaurin series expansion until we see a pattern emerging. So I'm going to start with n equals 0. So I'm going to have the nth derivative at 0, which is 1/3, over n factorial, in this case that's 0 factorial, times x to the n, which is going to be x to the 0. Let me color code it for you. So this is the blue part, that's the nth derivative at 0. This is n factorial, and then here is x to the n. So that's all part of n equals 0. Fabulous. Moving on to n equals 1. So the blue portion, the first derivative at 0, I'm taking it from here. It's going to be negative 1 over 3 squared over 1 factorial times x to the first. So this is the first derivative at 0. This is n factorial, which is 1 factorial. And then this is x to the first. How are we doing? All right, let's keep going. Plus, now we're going to work on n equals 2. So I have 2 over 3 cubed over 2 factorial times x squared. So here's 1, the factorial part, and then x raised to the n. Plus, one more, n equals 3. So we've got negative 6 over 3 to the fourth over 3 factorial, x cubed, 1, 2, 3. Okay, now you can keep going, right? There's infinitely many terms. But let's see if we can just pick up on a pattern so far. Okay. First things first, we have to decide where we want to start our sum. 0 seems like a natural place to me. Everything's looking good because we've got a lot of zeros going on in that first term, 1, 2, 3, etc. So let's start off with, we'll write this as the sum, starting at n equals 0, going all the way to infinity. Now, let's break down the blue portion, the nth derivative at 0. First thing I notice is it's alternating. This first term is positive, the second term is negative, third term is positive, fourth term is negative. So to make sure that my series is alternating, I need either negative 1 to the n or negative 1 to the n plus 1 in there. So let's see here. I'm going to put negative 1, since the first term is positive, I'm going to raise it to the nth power. And then when n is 0, negative 1 to the n is going to be positive 1, so that works out. Okay, what else do we notice? Well, we've got 3 raised to some power. Notice when n is 0, 3 is raised to the first power. When n is 1, 3 is raised to the second power. When n is 2, 3 is cubed. So whatever n is, 3 is raised to the n plus 1. It's always 1 higher. Do you see that? Okay, very good. Now there's one more portion going on in each of those blue terms in the nth derivative at 0. Look at the numerators. We've got 1, 1, 2, 6. Do you see a pattern with those numbers? Maybe, maybe not. I'll clue you in, and then now you'll be on the lookout for it, so maybe you'll notice it next time. So this is 0 factorial. This is 1 factorial. This is 2 factorial. This is 3 factorial. So in the numerator of each of those terms, we've got an n factorial. Okay, so this here in sigma notation represents everything from the nth derivative at 0. All right, notice in the denominator, in the purple portion, we also have another n factorial. So that's going to end up canceling out. And then the last thing, look at the green portion, x is raised to the n. Bada bing, bada boom. Okay, so everything's accounted for. Do you see that? And the more you practice these, the patterns will pop out at you more quickly. You'll notice things with the factorials. You'll be able to clean up really quickly. So what do I want to do from here? I'm just going to cancel out these n factorials, right? And then rewrite everything all nice and neat. So we have the sum, n equals 0 to infinity, negative 1 to the n, and then we have x to the n over 3 to the n plus 1. All right, how do we like that one? So. Okay, let's do another one. Example 2, we'll still work on Maclaurin series, okay? And in this case, f of x is equal to sine of 9x. So why don't you guys take a minute, pause the video, and then try to fill in the table yourself. So remember, you're going to have n, the nth derivative of x, and we're still doing Maclaurin series, so we're going to find the nth derivative at 0. Fill this in. I did about 5. N went from 0 to 5 when I worked on this. You'll see why in a second. So pause the video, fill this in, and then we'll compare our answers in just a minute. Okay, welcome back. So let's start off with n equals 0. That's just going to be f of x. So sine of 9x. And then sine of 0 is 0. Ooh, so we don't have a term there, right? Because 0 times anything is going to be 0. First derivative is going to be 9 cosine 9x. And I know cosine of 0 is 1, so 9 times 1, that's 9. Second derivative is going to be negative 9 squared sine 9x. And if I evaluate that at 0, I get 0. Third derivative is going to be negative 9 cubed cosine of 9x. Notice I'm not multiplying out those powers of 9. It's going to help me with finding the pattern when I want to write this in sigma notation. So leave it. And this is negative 9 cubed. Fourth derivative is 9 to the 4th sine 9x, which evaluated at 0 is 0. And then fifth derivative is 9 to the 5th cosine 9x, which is 9 to the 5th. So in this case, I took more derivatives because every other one was 0. So really, these are the only ones that are going to help me when I'm listing out each of the terms in my Maclaurin series to try to recognize the patterns. The others are gone. Oh no, don't worry. Okay. So sine of 9x, I'm not even going to mess with the 0. If you want to write it down, that's fine, but it's gone. Plus, now I have 9 over, remember, I'm going to have n factorial, so that's 1 factorial, and then x to the n, so x to the first. So here's the blue portion from the table. And then, how did I color code? Oh, purple and green. Okay. So this is the n factorial in purple and x to the n in green. Plus, so I'm just going to skip every other one. Then we have negative 9 cubed over, in this case, that matches up with n equaling 3, right? So you're going to have 3 factorial x cubed. Let's color code away. If it helps, I'm happy to do it. Plus 9 to the 5th over 5 factorial x to the 5th plus yada, yada, yada. Hopefully you see the pattern. If not, what do? You just keep taking derivatives until you can see it emerge. All right, now how are we going to write this in sigma notation? Well, these n's pertain to figuring out the coefficients of the terms. But when I write it in sigma notation, I'm going to have n represent something different. This is going to be for n equals 1. This is going to be for n equals 2. This is going to be for n equals 3 in my sum now, okay? So I'm going to start my sum at n equals 1 to infinity. Now let's see what's going on. Term by term. Let's work on the blue part. Again, this is alternating. Check this out. Positive, negative, positive. Okay, so I'm going to need negative 1. Be careful. Should it be raised to the n or the n plus 1? Well, since I'm starting here at n equals 1, it should be raised to the n plus 1. That way the first term comes out positive. Okay, very good. Now let's see here. The first term, I'm just looking at the blue portion, has 9 raised to the first. Then we have 9 raised to the third. Then 9 raised to the fifth. So it's always 9 raised to some odd power. Remember, if you need to represent an odd number, you can either use 2n plus 1 or 2n minus 1. If you want to represent an even number, then you just use 2n. So it looks like I'm going to have 9 to the 2n. Would it be plus 1 or minus 1? Let's see. If I want it to come out to be 1 on the first term, then it should be minus 1. Okay. Then in the denominator, we've got 1 factorial, 3 factorial, 5 factorial. So notice the factorial matches the exponent on 9. So it's going to be 2n minus 1 factorial. And then we have x raised to the same power, so it'll be x to the 2n minus 1. Okay, this is one option. Or you could start at n equals 0. Yes, I kid you not. So then that would be for n equals 1, that would be for n equals 2. So what would be different? We'll check it out. So we'll have the sum, n equals 0 to infinity. In this case, since the first term is positive, I want to have negative 1 raised to the n. Now for the exponent on 9 to be positive 1, if we're starting at 0, I'm going to need 9 to the 2n plus 1 instead of 2n minus 1. Check it. Check it. Look, if you plug in 0 for n, then you have 2 times 0 plus 1. Yep, 9 to the first. Then you have x to the 2n plus 1 instead over 2n plus 1 factorial. Now they both look equally complicated or clean, however you want to think about it. Typically we usually start at 0 though, so I would say I'd report this as my final answer, but there's nothing wrong with starting at 1 if that's what popped out at you, okay? And notice you don't have to necessarily, if you want to shift your index, you don't have to necessarily restart from scratch. You could have just said, oh, I want to start at 0 instead, so I'm going to lower where I start my sum from 1 to 0. And then to compensate, I'm going to increase the index by 1 in all of the expressions here. So instead of n, you would have n plus 1. So 2 times n plus 1 minus 1 would be 2n plus 2 minus 1, which is 2n plus 1, which is what we had here. So you can shift the index within a sum once it's already written if you like. Okay. That made it look messy. Let's clean it up. We want our final answer to be beautiful. Good, good. Let's do a Taylor series because so far we've only done Maclaurin and I don't want you to think that they're less important. That would be not good. Okay, so next example. Find the Taylor series generated by f at x equals a. And here for this problem, they're going to tell us f of x is equal to e to the 8x and a is equal to 3. So instead of a equaling 0, the way it is for Maclaurin series, a equals 3. All right, we're going to start the same way. So you have n, the nth derivative at x, and then in this case, the nth derivative at 3. Right? So now let's start taking some derivatives. This one should be fun. So if n is 0, you just have e to the 8x. And then plugging in 3 for x, this is going to be e to the 24th. All right, if n is 1, if I take the derivative, I'm going to get 8e to the 8x. If I plug in 3, that's going to be 8e to the 24th. Okay, let's take another one. Now I'm going to have 8 squared e to the 8x. So this is 8 squared e to the 24th. Do we need more? Let's do one more. So this is 8 cubed e to the 8x. So 8 cubed e to the 24th. All right, so let's start listing out the terms here. So f of x is going to equal, remember this is just one portion. So we have e to the 24th over n factorial. So that's 0 factorial. And then in this case, you're going to have x minus a to the n, so x minus 3 to the n. Here's the color coding. There's the factorial portion. There's the x minus a to the n. So that's for n equals 0. Plus, next term is 8e to the 24th over 1 factorial x minus 3 to the first. 1, 2, 3. Is it getting repetitive? If it is, that's fabulous. Then that means you're picking up on the pattern. Plus 8 squared e to the 24th over 2 factorial x minus 3 squared. Let's do one more. Let me scoot this over. I feel like we're running out of space. Oh, much better. Plus 8 cubed e to the 24th over 3 factorial x minus 3 cubed plus yada, yada, yada. Okay, let me highlight all of the portions of the coefficient that came from the table. Here's the n factorial that you always have. And then here's x minus a to the n. Love it. All right, so let's write this in sigma notation. Looks like it makes sense to start at 0 all the way to infinity. Now let's see, what pattern is going on with the blue portion, the nth derivative at a? I've got e to the 24th in every single term. That's not changing, that's just constant. Let me highlight it in a different color. Look at this, what is this? E to the 24th, e to the 24th, e to the 24th. Okay, that's not changing, that's just a constant. He's minding his own business. Then notice on the first term I've got, look how slick. This is 8 to the 0, 8 to the first, 8 squared, 8 cubed. So it's 8 to the n. Blue portion taken care of. Boom. Over. Let's look at the purple portion. 0 factorial, 1 factorial, 2 factorial. What's that going to be? Why, yes, it's n factorial. And then lastly, the green portion, we've got x minus 3 to the 0, then 1, then 2, then 3. So it looks like that's x minus 3 to the n. Fabulous. Good, good, good. Okay. That's it for using the definition. Now I wanted to show you another kind of exercise you might run into. And the directions would say something like this. Use a known Maclaurin series to obtain the Maclaurin series for the given function. Okay, so what that means is you can use a known Maclaurin series. The known Maclaurin series I mentioned in my video lecture that I linked earlier. I can link it again right here. So you want to memorize the Maclaurin series representation for sine x, cosine x, e to the x, obviously 1 over 1 minus x, tan inverse of x if you're feeling fancy, natural log of 1 plus x. Okay, put those all to memory. Because for these exercises, you basically don't have to start from scratch. You can use a known one to come up with a new one. What do I mean? So for example, we're given f of x equals sine of 3x over x. So instead of listing out all the coefficients and making a table, you say, oh, well, we know that the representation for sine of x as a Maclaurin series is the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Yes, you just memorize that. It's the easiest way to memorize it is you go, oh, sine's an odd function, so check it out. That's an odd number, and that's an odd factorial. Boom. So what do you do with this? Well, you say, I want f of x to be sine of 3x. So first let me adjust accordingly. So sine of 3x would be the sum, n equals 0 to infinity, negative 1 to the n. Instead of x, I'm going to put 3x to the 2n plus 1 over 2n plus 1 factorial. And then I can clean that up a wee bit. Let's just distribute the exponent. So we have the sum n equals 0 to infinity, negative 1 to the n, 3 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. So this is Maclaurin series representation for sine of 3x. How is that different than f of x? I have one more thing to take care of. I need to divide this by x, which is the same as multiplying by 1 over x. And what that means is now one of these x's is going to cancel out. So I'm done. So sine of 3x over x is equal to the sum, n equals 0 to infinity, negative 1 to the n, 3 to the 2n plus 1, x to the 2n over 2n plus 1 factorial. Okay. Let's box it nicely. We're rather proud of this. Okay, good. Let's do one more like that. I'll call it example 2. In this case, f of x equals x times cosine of 1/2 x squared. Okay, do you remember the power series representation for cosine of x? Here's the easiest way to remember it. Cosine of x is an even function, right? So we know. So it's going to look just like sine for the Maclaurin series representation. It's just instead of 2n plus 1s, it's going to have 2n. All even exponents and even factorials in the denominator. So it's the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. Okay, so start bit by bit. We need to manipulate this so it matches f of x. So I'm going to replace x with 1/2 x squared. Okay. So cosine of 1/2 x squared is going to be the sum, n equals 0 to infinity, negative 1 to the n. I'm going to have 1/2 x squared to the 2n over 2n factorial. And then the only thing I'm missing, let's just get this show on the road, is this x here. So let's multiply by it. Bam, add it in. Okay, now it's cleanup time. So we've got the sum, n equals 0 to infinity, negative 1 to the n. Let me put it over 2n factorial because all the spicy action is going to happen right here. I'm going to distribute the 2n through. So we have here 1/2 to the 2n, and then x squared to the 2n is going to be x to the 4n, and then I have another x. Do you agree? Okay, so last step, I can write this as the sum n equals 0 to infinity. What's going to be in the numerator? So I have negative 1 to the n. Look, this is pointless. 1 to the 2n, that's just 1. I'm not even going to write it out. Then I have 4n and x to the first, so that's going to be x to the 4n plus 1 over, now here this is going to be 2 to the 2n in the denominator, and I've got that 2n factorial. Beautiful, we're done. Okay, so hopefully this will help you when you're working on your homework or just cranking out some exercises. You can really get in it. Be sure to give the video a thumbs up, subscribe if you haven't, share it with your classmates and your friends, and leave me comments below about what other sorts of videos and things you need help with. I'm more than happy to make more videos for you guys.